Hello. In this video, we're going to finish up chapter 5 and look at the average value of a function. So let's get going. How do we compute the average temperature during a day if infinitely many temperature readings are possible? And you can see in the graph what's going on here. So what does it even mean to have an average temperature for a whole day? So you can see that, so for example, on a cold day, like it is here in February, these would be the temperature readings, and you can kind of estimate where does the function look like the area under the function from 0 to 24 is the same as the area under this curve, when in fact, remember, this would be even like a negative temperature. So what does it mean to sum a bunch of temperatures? So we're going to make that all explicit in this section. So the idea is we know what it means to have an average value of a function on an interval by just looking at the endpoints. But you saw it in like college algebra, but I don't think you've seen it in calculus yet because you don't do this stuff in Calc 1. So we have a function defined on a domain, and you take the domain AB, divide it into n equal subintervals, each with length delta x. This is how we built integrals in a Calc 1 class back in chapter 4 in this textbook, or if you used a different book, maybe it was a different chapter. But you can think of it as, let's say you want to find the average temperature for a whole day. Maybe you break it into 24-hour intervals and you take a reading once per hour. So that's the idea. And then you choose points in successive subintervals, and you just take the average of those numbers. So if you were trying to do temperature and you took 24 readings once per hour, and it doesn't have to be like on the half hour or on the hour, it could be just anywhere in the interval, took 24 readings and add them up and divide by 24, you would get something like the average temperature. And that's what this says here, right? So this is, let's say there are 24 temperature readings, so n would be 24. So you'd have f of x1 star. So in the first hour, you take one reading. Again, the star just means any point in the interval. So whatever the function is there, and you go all the way up till you do f, let's say 24 star divided by 24. So this is just the formula for a mean. But we know what n is, right? We can see using this formula here that n is just, if you take this formula, multiply both sides by n and divide both sides by delta x, you get n is delta x in the denominator and b minus a in the numerator. So I'm just going to replace n with b minus a over delta x. What I want to do is get the n out of there. Okay, well, when you divide by a fraction, you flip and multiply. So the delta x goes in the numerator, and the b minus a goes in the denominator. So I can factor this out. So I have 1 over b minus a times the sum of the function values times delta x. Then I distribute the delta x. And so what we have here is a bunch of rectangles of this height, right? This is the width of the rectangle. So if you're doing temperature readings, this would be like 1 hour if you're doing 24 hours in a day. So this would be the temperature times 1 hour plus all the other temperatures times 1 hour till you get to the last temperature reading times an hour. And then you divide by the width of the interval, right? B minus A is just the overall width. Once again, you factor this thing out to the front, and you have just this sum. Well, this Riemann sum right here is exactly the formula for the definite integral. So you just take this whole thing, leave the 1 over b minus a out front, and multiply it by the definite integral. And that gives us this formula. So if n increases, we're computing the average value of a large number of closely spaced values. For example, we would be averaging temperature readings taken every minute or every second. So if we started off with 24 temperature readings and you wanted to make it more accurate, you could take a temperature reading every minute, right? So you'd have 60 times 24 readings, or every second. 60 times 60 times 24 readings. And eventually, the width of those rectangles is so small that you're basically doing an integral. And that's what this says here. So that's the formula we're going to use, and that's the definition of the average value of a function. It's a really easy formula to remember. You're just doing a normal integral, but you're dividing by the width of the interval. So you're just dividing by b minus a. So that's it. Let's see an example. So find the average value, h, on this interval. So our function is cosine to the fourth x times sine x. Our interval is 0 pi. If you want to graph these things on your own, you can. You're not required to draw graphs because we're not doing any rotations or anything. But if you wanted to graph it and sketch it, that'd be fine. I'm not really going to do that in this problem. So, here's a, here's b. So we're going to divide by 1 over b minus a. So 1 over pi minus 0. The integral 0 to pi cosine to the fourth x sine x dx. Well, we know how to do this integral, right? This is a u substitution. So cosine is u. So du is negative sine x dx. We have sine x dx. We don't have negative sine x dx. So multiply both sides by negative 1. And then make sure you change your limits of integration. So when we rewrite the integral, we're going to plug 0 into here, and we're going to plug pi into here, and that's going to give us our new limits. So it's 1 over pi is out front, and then cosine of 0, cosine of pi. I'm not going to solve those yet because I want to show all the work. The u substitution, cosine to the fourth becomes just u to the fourth. Sine x dx is negative du. So all I'm doing is plugging everything in. Don't try to solve it in one step. Just keep track of your steps. I distributed everything. So I distributed this negative and pulled it to the front. Cosine of 0 is 1. Cosine of pi is negative 1, which leaves me here. I don't like having smaller numbers at the top and bigger numbers at the bottom. So I'm going to use the property from Calc 1 that says I can switch these two if I make this negative. Well, it's already negative, so it just flips the sign and makes it positive. So switching the bounds of integration flips the sign here. So that's what I do next. So it's just 1 over pi from negative 1 to 1, u to the fourth. But I'm not done yet using properties. I'm going to use properties of even functions. This is a polynomial with an even exponent, so it's an even function, which means I can replace the lower limit. If the integral goes from negative a to a, which it does, I can replace the lower limit with 0 and double the integral. So that's what I'm doing here. I go from 0 to 1 and multiply by 2. That was covered at the end of section 6.7, I believe. So if you want to go review, you're allowed to use even odd properties. In fact, for integrals like this, it's way easier. Just memorize which functions are odd and which ones are even. So that, again, that's a polynomial with only even powers. This is a much easier integral to do, right? It's just 1/5 u to the fifth. Plug everything in. I pulled the 5 in the denominator out front here. And you're done. And that's the answer. So as you can see, pretty typical sort of problem from it turns into a Calc 1 problem fairly quickly. The only thing that makes this a Calc 2 problem is just knowing when to use the average value. So what this is saying is that if you drew the graph of this if you drew the graph of this function on this interval and then drew a horizontal line at y equals 0.127, that the area in that rectangle would be the same as the area under the curve. That's all it's saying. And that's something you can verify on your own. So go ahead, if you want to give it a try, go ahead and give it a try. You don't have to do it, but if you like sort of visualizing how this stuff works, that's a good opportunity to do it. It's similar to the picture at the beginning of this presentation. There's a picture of it. Okay, now we're going to do the mean value theorem for integrals. There's only 2 topics in this section. So this is the second topic. So basically what this is saying, so the mean value theorem was about y values. This is about y values, but in a different way. So if you forgot the mean value theorem, you might want to drag out your Calc 1 notes and check it out. This is just an extension of the mean value theorem, but we're doing it for integrals, not for functions. So if f is continuous on AB, then there exists a number c in AB such that the function value at c is the same as the average value of the function. Right? So we're just saying that the function takes on a value where if you draw a horizontal line, then the area of the rectangle is the same as the area under the entire curve. That's all it's saying. In fact, you can take this expression and multiply both sides by b minus a, and you get this expression. Right? This is the integral itself. This is the height of the rectangle, and this is the base. So that's what this is saying, right? This is a x-coordinate. B minus a is a measurement in the x direction. F of c is a measurement in the y direction. So if you multiply them together, x times y is a rectangle. So this is a statement about the area of the rectangle. I'm just saying the area of the rectangle is the same as the value of the function. So the area under the curve of the function. And there's the picture, right? So I just went over this, but I'll read it. And if you remember the mean value theorem and the intermediate value theorem from Calc 1, then this will make more sense. It's basically saying if this function is continuous, that there has to be some horizontal line somewhere, and that line intersects the curve at some number c. It can intersect more than once, but they're saying there's at least one. Because it's a horizontal line. It can intersect as many times as you want. And just looking at the graph, it certainly makes sense. For any curve, and you're finding the area between the curve and the x-axis, that you can just move this thing up or down until the area under the curve is the same. So the red area under the rectangle is the same as the blue area under the function. And the other way to think of it is this here. You can chop off the top of a two-dimensional mountain at a certain height. You chop it off at the average value, and then you just take what's left over and push it over into the valley so the mountain becomes flat. This is definitely a sort of mnemonic way to remember what it does. So that's where the term mean value comes from, just average value. All right, so let's do one of these types of problems. Find all numbers b such that the average value of f of x equals 6 plus 10x minus 9x squared on the interval 0b is equal to 7. So think about what this is saying, right? Here we have a parabola, right? It's an upside-down parabola. And the idea is, if you draw the graph of this and start at 0 and move one way or the other, there is at least one place, because the mean value theorem says that there's going to be at least one place. But there might be more places where the area under the size of the rectangle you draw as you move b one way or the other, that the area is the same as the area under the curve so far. Again, you don't have to draw these out, but if you want to just go ahead and type that into your calculator and look at it and see what it looks like, feel free to do that. But we're just going to use algebra to solve it. So there's the formula for average value of a function. I plug in everything. So b just stays b for this problem. A is 0. It's the integral from 0 to b of the function. So you simplify what's out front. 1 over b minus 0 is 1 over b. Go ahead and just do the integral. Right? You can see clearly that this is, in fact, just the integral of this. Plug in b. And then, according to the way the problem's set up, we set it equal to 7. So we just want to know what values of b give me a rectangle of size 7. Because they're saying that the average value is like the line y equals 7. And the function itself will also have area 7. So simplify, quadratic formula, or complete the square. Both of these are positive numbers. And you can see what's going on there, what it looks like. So that's it. Quick note about this problem. On the homework, for stuff like this, you have to type in exact values. You can't use decimals for this, so make sure that you are fully solving this thing out with quadratic formula or completing the square. If you have some of the graphing calculators, some people have programmed it to solve the quadratic formula, but you have to have exact values, so make sure you're doing it by hand. All right, well, that's it for this video. Told you it was a pretty short video. And you won't be watching any videos for a little bit because this is the last section before the exam. So hopefully you're watching this at least a week before the exam, so you have lots of time to study. As always, if you have questions, post on the discussion board or just send me a message. And that's it for today. Have a good day, and I'll see you next video. Bye-bye.